Next, we're going to start looking into problems that may ask us to solve for the empirical or molecular formula. So before we get into those problems, we have to know what do they even mean by those terms. So the molecular formula is the one that we're very familiar with. Okay, it tells us exactly how many atoms are in a molecule. So for example, if you take the molecule C6H6, it tells us that in one molecule of C6H6, there are 6 carbon atoms and 6 hydrogen atoms. So the molecular formula is the one we've seen most commonly before. Now the empirical formula is when you take the molecular formula and you divide by the greatest common factor. So the empirical formula, you can think of it as like the smallest unit of a molecular formula. So that means if we took this C6H6, which is our molecular formula, and I'm now interested in the empirical formula, I see that the largest number that goes into both 6 and 6 is just 6. So I would divide both of those by 6, and my empirical formula would be CH. So there's invisible ones there, but we don't write those in. So the empirical formula is just CH. It's the smallest possible unit of atoms for that molecule. Okay, so now for the problems where we're trying to figure out the empirical formula from a combustion reaction. Okay, so before we actually go into an example, let's go over the steps since they're slightly different from the steps we learned before, but using the same kind of general ideas, we can make sense of it. So in these types of problems, first of all, we usually be given the mass of the hydrocarbon. Remember, that's something like CHO. We don't know the subscripts, but we know it's something like that. And you'll also be given the mass of carbon dioxide and the mass of water. Okay, so those are usually the 3 things you're given, and you want to figure out what empirical formula does our actual hydrocarbon have. So remember from previous empirical formula problems, our one goal, we said, was to figure out how many moles of each atom there were. So that means we wanted to figure out moles of carbon, moles of hydrogen, and moles of oxygen. So here, the way we do that is just a little bit different since we're given different information. So the first thing you want to do is, you see that we were given this mass of carbon dioxide. So let's just focus on carbon dioxide first. If I actually find the moles of carbon dioxide, I can actually find the moles of carbon in our hydrocarbon. So that will actually tell me the moles of carbon in the hydrocarbon. Okay? And it's actually going to be a 1-to-1 ratio. So for example, if I found 2 moles of carbon dioxide, that means I have 2 moles of carbon. Okay? And that gets us one step closer to the problem since we're trying to figure out moles of each of these atoms before proceeding. Next, you can do the same exact thing with water. So that's kind of nice. So if you find we're given the mass of water, you can then find the moles of water, and then using the moles of water, you can figure out the moles of hydrogen. There's just one difference here where notice that when you have moles of water, for every 1 mole of water, how many moles of hydrogen are present? So for every 1 mole of water, there's actually going to be 2 moles of hydrogen because there are 2 hydrogen atoms in each water molecule. So using the moles of water, we're still going to be able to get the moles of hydrogen by multiplying by 2 pretty much. So now we'll also be able to get the moles of hydrogen. So we've now figured out the moles of H here. Great. So the last thing we want to figure out is the moles of oxygen before we can proceed like any other regular empirical formula problem. But we weren't actually given any information on oxygen. So what we would do now is, remember that we were given the mass of this total hydrocarbon, and we also know the moles of carbon and the moles of hydrogen. So what we'd actually do now is figure out what mass of carbon is there based on the moles, what mass of hydrogen is there based on the moles, subtract those masses from the mass of the hydrocarbon to figure out the mass of oxygen. Okay, so we first figured out the mass of carbon and mass of hydrogen, and we do that only to figure out the mass of oxygen. Now, Finding the mass of oxygen then allows us to solve for the moles of oxygen, which is a very key step, because now we have moles of each of those atoms that make up our empirical formula. So now you just continue like a regular problem. So you have moles of each carbon, hydrogen, and oxygen atoms, and you're going to divide by the smallest number of moles, and that'll tell you how many of each atom there should be in the empirical formula. Okay, so now let's go try out an example and give that a try. Okay, so we're told that 55.4 grams of a compound containing only C, H, and O was burned in the air to produce 143.2 grams of carbon dioxide and 68.4 grams of water. And we're asked to determine the empirical formula of this compound. So right away, we should know that this is a combustion problem, right? It's saying that we have a compound with C, H, and O. We said that's a hydrocarbon. It's being burned in the air. That's another big clue that it's a combustion reaction. And then we're producing carbon dioxide and water, which we know is part of the combustion reaction. So the first step, we can figure out the moles of carbon dioxide, and we'll use that to figure out the moles of carbon. So using our equation n is equal to little m over big M, we'll take the mass of carbon dioxide that we were given and divide that by the molar mass of carbon dioxide. So once I've solved for my molar mass, I can go ahead and finish that calculation to solve for moles. And I get 3.254 moles of carbon dioxide. Okay, and we said that based on those equations, we know that the carbon in the hydrocarbon has a 1-to-1 ratio to carbon dioxide. So this will actually be the same number of moles of carbon in our hydrocarbon. So we actually also have 3.254 moles of carbon in our hydrocarbon. So I'm going to put this in a box since this is actually really important. Later on, we're going to need to come back to this moles number. But for now, we're going to continue trying to figure out the moles of each of the other atoms for hydrogen and for oxygen. So let's do hydrogen next. So we're going to figure out the moles first of water, since that's what we were given. We were given the mass of water, so we can figure out the moles. So I'll plug in the mass of water, 68.4 grams. We're going to divide by the molar mass of water. And we get 3.7968 moles. Okay, so now I have to figure out how many moles of hydrogen are present in the hydrocarbon. So if we take 3.7968 moles of water, for every 1 mole of water, we said there are 2 moles of hydrogen. Okay, because there are 2 hydrogen atoms per water molecule. So now I'm able to solve for the moles of hydrogen, since the moles of water, those units, cancel out. So now the moles of hydrogen are 7.5937 moles. So we've again found the moles of another element we're interested in, so I'm going to put that one in a box. We're going to have to come back to that. And now we have to go back and figure out, how can I find the moles of oxygen now, the third element that we're interested in? So we were given the mass of the overall hydrocarbon, cool, and we have the moles of the other atoms. So what I can do is find the mass of these other atoms and then subtract them from the overall mass of the hydrocarbon, and that'll help me find the mass of oxygen. So just to make sure that we're all on the same page, this is what I'm doing. I'm using this calculation. The mass of the hydrocarbon, which again is made up of carbon, hydrogen, and oxygen, is equal to the mass of carbon, the mass of hydrogen, and the mass of oxygen. Okay, so I'm going to need to solve for the masses of carbon and hydrogen, and I'm given the mass of the hydrocarbon, and then I can solve for the mass of oxygen and then use that to solve for the moles of oxygen. So I now have moles of each of our atoms. So let's go ahead and solve for the mass of carbon and hydrogen. So we're going to use the equation. So we're going to use the equation n is equal to little m over big M, we'll rearrange that to solve for the mass. So mass is equal to moles times the molar mass. So we're going to plug in our moles and multiply by the molar mass. And you get 39.08 grams of carbon. Now for hydrogen, we're going to use that same equation. We're going to take the moles, 7.5937 moles, and multiply by the molar mass of hydrogen. And we get 7.65 around there grams of hydrogen. So now we have the mass of carbon, the mass of hydrogen. Let's go back and see what the mass of the hydrocarbon was. It's 55.4 grams. So we're just going to plug those in and solve for the mass of oxygen. Okay, so let's rearrange first to solve for the mass of oxygen. It's going to equal the mass of the hydrocarbon, subtract the mass of carbon, and subtract the mass of hydrogen. So we're getting 55.4 grams for the mass of the hydrocarbon, minus the mass of carbon, which is here, 39.08 grams, minus the mass of hydrogen, which is 7.65 grams, and that's going to give us the mass of oxygen. So I get 8.67 grams of oxygen. Okay, so now I have the mass of oxygen, but remember for these empirical formula problems, I need to find the moles of each atom. So I have the moles of carbon over here, the moles of hydrogen, and finally I need to find the moles of oxygen before I can go on and figure out the empirical formula. So the moles of oxygen, again we're using N is equal to little m over big M, where the mass is what we just solved for, 8.67 grams, and the molar mass for the oxygen atom is 15.999 grams per mole. Just to clarify, we're only dealing with the oxygen atom, so this should just be oxygen. This would be mass of the oxygen atom, okay, since the oxygen atom is a part of that hydrocarbon. So when you solve, you get 0.542 moles of oxygen. Okay, and now we're going to go ahead and put that in the box as well. So now we have moles of each of our elements, and we want to figure out the empirical formula. So in order to do this, we're going to divide by the smallest number. So which of these is the smallest number? So the moles of oxygen atom is the smallest number. Again, that should just be the atom, so no subscript. Okay, so now we're going to go divide all of those three numbers by 0.542. So when I divide oxygen's number of moles by 0.452, I just get 1. For hydrogen, I get 14. And for carbon, I get 6. So now we're going to use these numbers to determine what our empirical formula is. So it would be, the empirical formula is C6H14 and oxygen with a subscript of 1. Okay, so that is our final answer for our empirical formula. Again, we followed the steps where we first found the moles of carbon dioxide, used that to find the moles of carbon. We then found the moles of water, used that to find the moles of hydrogen. And then we knew we had to figure out the moles of oxygen, but first we found the mass using the mass of hydrocarbon and the masses of the other atoms. We were then able to find the mass of oxygen and then the moles of oxygen as well. And then once we had the moles of each of those atoms, it became just like any other empirical formula problem where we divide by the smallest number, and that gives us our empirical formula over here.
Want more bite-sized lessons? Check out the Wise free trial at wizeprep.com. Oh, and subscribe to our YouTube channel while you're here.